Today we're going to talk about the Rutherford and Bohr model of the atom. Back in the day, believe it or not, most people didn't know what an atom was, and many early Greek scientists thought that you could divide mass an infinite amount of times. Now we know that that's not true nowadays, so let's jump right in. Rutherford was responsible for discovering the nucleus. One of the things he did to later become named the father of nuclear physics was he did a famous gold foil experiment. You may have seen this before. What we have here is a gold foil, and then it's surrounded by a phosphor screen almost at 360 degrees around it. And you have a source that emits alpha particles at very, very high speeds through this gold foil. These alpha particles have an energy of about 5 mega electrovolts, and they are very, very fast. Based on the knowledge that they had of basic momentum, that because of how fast this was going to go through, they thought it would be like a bullet shooting straight through paper. Maybe you would get very slight deflections in the pathway, but you didn't expect much. This was the assumption they made based on the current model of the atom that was accepted at the time, which was the plum pudding model. The idea here is that they had discovered electrons, which were negatively charged, so they knew that there was some kind of a positively charged substance or thing in the atom to keep the electrons in. As such, they compared it to a positive pudding-like substance holding in the plums or the electrons. So they expected deflections of the alpha particles due to the electrons, but nothing more. However, after running this experiment quite a few times, what they saw was that yes, there was quite a few deflections in different directions through the gold foil when those alpha particles were shot through, but there was occasional times when the alpha particles would come back the same direction from where it came. Here we see kind of an example of the atoms that are present. Imagining this is the gold foil. You have the atoms, and they're about 10 to the negative 10th meters apart. And the nucleus, which was later found, is about 10 to the negative 15th meters across. The difference in size is drastic. As you see these alpha arrows going through, they get slightly deflected, but the occasional one will hit the nucleus and return back at almost the same direction it came. When Rutherford saw this, he was shocked. He said that this was not the kind of idea that they had of the atom. They didn't imagine that most of it was, in essence, empty space. He said it was so shocking that it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So this was a big deal. What they ended up finding as a result of these experiments was that they had this mass positively charged in the middle of the atom that was very, very small, almost 100,000 times smaller than the atom itself, but with a huge density of 10 to the 15th grams per centimeter cubed. That is unlike any other macroscopic matter that had been discovered or quantified back in the day. As a result, Rutherford came up with a relatively revolutionary model of an atom. He called it the planetary model of the atom. What you had here was the positive nucleus with orbits kind of like in the solar system where the electrons would be surrounding it. This kind of model still was incomplete. It wasn't the correct or most up-to-date model that we have today. So this is where Bohr enters. Bohr was actually a young scientist who went to Rutherford's lab, and he saw almost immediately as these things were published these new and upcoming ideas about the atom and its structure. However, Bohr questioned the planetary model of the atom because of specific classical mechanics and equations that were derived at the time. They knew that the electron would have to be releasing electromagnetic radiation while orbiting the nucleus. In doing so, the electron would slowly lose energy and spiral inwards, crashing into the nucleus. This suggests that the atom, by nature, is unstable. There was another mystery at the time of the atomic spectra, which was that atoms would release a spectra of certain colors, or in other words, certain wavelengths. And because of Einstein's proposal of photons, with energies proportional to their wavelengths being a result of these colors, people understood the math behind it and derived equations, but they didn't have any data that supported a workable theory that would really explain the phenomenon of the spectra of atoms. What Bohr ended up doing is he was able to define hydrogen spectrum wavelengths. With this equation, he was able to correlate the wavelength of the emitted electromagnetic radiation, and with this constant, the Rydberg constant, which is 1.097 times 10 to the 7th inverse meters. And he related those to these specific series that had currently already been found, which were in essence related to the spectra of the hydrogen atom at the time. And he derived the correlation of the change in energy equaling HF, which is the energy of the absorbed or emitted photon. The idea here is that an electron lived in a certain orbit around, and that orbit had a specific energy, and that each of the subsequent orbits had different energy levels. As you jumped up to a higher energy level as an electron, that means you absorbed the specific energy of that energy gap. That was the photon that was absorbed. Likewise, if you were to jump down a level, a photon would be emitted with that exact wavelength or frequency that would correspond with the energy difference between the two orbits. This energy level diagram is a convenient way to display the energy states, and this was a new idea. No one had ever figured out how the spectrum of atoms came about, and the idea of energy levels for electrons had yet to be derived, and Bohr was the one to do so. There are limitations to Bohr's theory, however. One of the first ones is that he derived his equations based off of hydrogen. As we know, all atoms exhibit different properties. All atoms have different number of protons in their nucleus, and many times different number of electrons as well. Those values play a big part into how the amount of energy and the type of spectra that an atom contains. As such, he derived equations for hydrogen-like atoms. Another limitation to his theory is the idea of electron orbitals, while more accurate than what had been presented before, are not completely what we know to be true today. We know now that electrons really more likely exist in clouds of probability. There's not well-defined orbits. That being said, his work revolutionized and defined that electrons were quantized. As a recap, Rutherford and Bohr and their models of atoms were key steps in the progression of our knowledge of the current model of the atom.